maybe two different surveys and looking at whether we can mix them together and confer us. Is that?
Yes.
Okay, thank you. We've got about 15 minutes and then maybe a little bit of time at the end for questions.
Okay.
Thank you.
So, thank you all for inviting me. I'm not sure exactly what level to pitch the talk at. Sophie invited me to give a talk, so I will. It's based on, I did this work with Andrew Cheshire, who's also in the economics department a few years ago. We were doing some work for DTI just to review. They had a bunch of data sets they wanted to match to look at impact of various government policies on productivity. And they just wanted to know, what does the literature have to say about the statistical properties when you link of a linked data set. So we did a bit of a literature review, and so what I'm going to talk about today, I'm not going to provide any precise details really. So I guess most of you are quite technically minded, so if you want precise details, that's not going to be in today's talk. It's just really a high-level overview. I'm not doing any active research on this area, but I mean, a lot of the other research I'm doing, I'm pretty much always in a situation where a single data set doesn't have all the information I need, so you need to match the data sets and then think about these issues. And the basic issues are quite simple, and I think that will come out as a talk. So when you link data sets, there's three major sets of statistical issues that arise. Survey design issues. The gold standard of a survey would be a randomized sample, so you don't have to worry about weighting or anything like that. But most surveys, because of cost issues, are complex survey designs. So it's either a stratified random sample or sometimes even non-probabilistic sampling or choice-based sampling. And so because it's not a simple random sample, if you want to conduct precise statistical inference about the properties of the population, oftentimes you need to wait. You don't always need to wait. Sometimes even if you don't have a random sample, you don't have to wait, but oftentimes you do need to wait to get precise estimates of features of the population. So that's an issue with any statistical exercise, is weighting the sample. It becomes more of an issue when you link data sets, because it's not always obvious what the statistical properties of the linked data sets are. So you might have one complex survey design stratified based on one set of variables, a second data set stratified based on another set of variables, and then when you link them, you might some records might not be linked properly, or there might be problems in linking, and so the final survey design of the resulting sample is not always obvious. If you're going to design a survey in advance and you know that they're going to be linked, there's some ways you can design it so that it becomes easier to link, so you know you can control the properties of the final survey. But usually, at least in most of the applications I look at, I'm given some data and I need to link them. I can't design the survey. Second set of issues is measurement error issues. In addition to non-representativeness of the sample, when you link with any survey, there's always measurement error issues. You measure a particular quantity that you're interested in. It's measured with error depending on the survey instrument or the measurement instrument. When you link data sets, additional measurement error is produced depending on the linking process, and I'll talk about that in a little bit. And then finally, information loss. If you link two surveys, what do you do? Suppose there's some records in one survey on say census tracts or census statistical areas, and the second set of survey has zip codes, and you link them, and some of them you can't find a match in the other data set. So what do you do with the records that aren't matched? You can throw them out. If you have a large enough sample, and under certain conditions, you can throw them out without any bias in your estimates, but you lose information because it's, if you have data, you'd like to make use of it if you can. So in each of these categories, the solutions for the problem are well known in the statistics literature, but depending on the particular thing, if you're trying to estimate a very highly nonlinear model, and you have a complex survey design with complicated weights, particularly if you have choice-based sampling. Choice-based sampling is if the sample is based on the outcome, if the sampling design is based on the outcome and not on the inputs. And then in choice-based sampling, the sample you have is not going to be representative of the population, and the way in which it's not representative is going to depend on the outcome. In principle, you can still estimate consistently properties of the population, but it's not like technically demanding, it's computationally demanding, and whether it's feasible or not depends on the application. So it's either computationally or technically demanding, or you need information, for example, with measurement error. If you know what type of measurement error there is, suppose you know that it's classical measurement error, it's just mean zero, it's independent of everything and has a variance that's known, then there's a lot you can do to correct your estimation procedure. But if you don't know the measurement error process, there's limits to what you can do. And if you don't know anything at all about the measurement error process, then what people often do is resort to imposing assumptions, which you need to establish whether they're true or not. Okay. This repeats some of what I just said. Anything new on this slide? I think I said all these things already. If in a particular application, because of you have two sets of data sets that are linked, and you don't know what the resulting survey design is, how representative it is of the sample, what can you do? Well, the simplest thing you can do is compare the means and variances of the variables in your data to other outside sources and see whether they match up. That's not a perfect solution, but that gives you some confidence that you have a sample that can be made representative by proper weighting. Or if you think that in particular question of analysis, the data you have is hopeless, then you just need to get better data. And so that's, if you have resources to do that, obviously that's a very good solution. So how does measurement error arise in these situations? Well, if you're linking two data sets, for example, based on, in some labor economics studies in the United States, people were linking United States Census records and United States Social Security records. So Social Security is like the national insurance system. And they were linking based on Social Security numbers, which presumably every person in the country who works in the country has a Social Security number and is measured without error. But every time somebody starts a new job, somebody fills out a form, there's lots of coding errors in copying the Social Security number to the data set. So when you try to look at, say, unemployment at the weekly or very high frequency level, it becomes very difficult because a lot of what looks like people losing their job is somebody just changing the Social Security number because it was recorded with error. So if you're trying to link two data sets based on Social Security numbers, you might just fail to match people or you might match person 1 to person 2 even though they're not the same because there's measurement error in the variable on which you're linking. If you match two records that are not the same observational unit, that's going to bring measurement error. So if you want to say, in a housing market context, I've been doing some work matching American housing survey data to US Census data. And there you want to match based on the census tract. You want to match a particular housing unit to a particular census tract. And if you match to the wrong census tract, then you're going to measure the geographic variables around that house incorrectly. Now, if you're just commissioning a survey and you're picking up information from some particular social science or economic or social situation, you can, to some degree, you can control the measurement error because you can test out the survey instrument. But when you're linking data, it's often hard to control the error. And so wherever you have measurement error in a survey instrument, the problem is much worse in a data linking environment because you don't necessarily know the properties of the measurement error. Similarly, in many-to-one matching, so again in labor economic situations, you often have data sets on firms. So firm is a big national entity, and you're going to match that to data on plants. So a firm might have 100 plants, and you want to use capital measured at the firm level, capital investment measured at the firm level, to impute somehow the capital investment at the plant level. So that's going to bring in measurement error because you don't know how much capital they invested in each plant. So what can you do when you have measurement error problems? So the first solution really is to find out in your data environment everything there is to know about the measurement error. And then if a lot is known, then there's lots of techniques that can be used to correct the measurement error. As I said, if you know it's classical measurement error with a known variance, essentially you can do a Taylor expansion of your regression model and correct for the error. If it's a nonlinear model, you can do something quite similar. If you know, there's been a lot of recent work in the econometrics literature looking at, suppose you know, for example, that you have some variable, it's measured with error, but the mode of the distribution of the true variable is independent of a measurement error. So knowledge of that type of fact, which perhaps could be garnered from a different survey or some study of the properties of the measurement error, can be quite useful. But again, that relies on the knowledge that the mode of the distribution of the true variable is independent of the measurement error. If you don't know that's true, then you have difficulty identifying what you're trying to identify. Okay. So what do we mean by information loss? So if you're matching two data sets and you throw out records that are not matched, then you lose information. So in some cases, maybe you can, instead of throwing them out, you can use those unmatched records to provide some information for your estimation problem. If you have a record and you link it to if you have information on one unit and you link it to the wrong unit, then you're going to attribute the information from the unit 1 to unit 2 when it should be kept on unit 1, and that can also lead to data loss. And here there's a lot in the econometrics literature. Again, in the past maybe 5 years, there's been some research on how can you do analysis when you have some records that are matched and some that are unmatched. There's some things you can do, but the impact of this type of problem on on the final design of the survey is unknown, really. Okay, so that's kind of again, this talk is not really going to be very precise about any detailed problems about data linkage, just giving you some of the high-level issues. And now I've given you a very high level. Now I'm going to give you a slightly more detail about survey design, types of data linking, survey design, measurement error. And when we did this work, we were looking at particular matching of some labor market data sets, in particular data on firms from the ARD survey, and data on workers. And so in this paper we reviewed some specific literature that studied the properties of linked data sets in that context. But I think I'm probably not going to talk about point 4 very much. Okay. So it's a little bit useful to categorize different types of linking. So one type of linking is, we've called it direct record linkage. So you have an identifier, perhaps a physical address of a building or of a ship, and you have information on the building in one survey. You have some information in one survey. You have some information in another. For example, in the housing context, you might have the address and value of a house in one survey. I didn't write that on here. And you might have in a separate survey the address and information about the quality of the housing unit, or about investment in things like energy efficiency or an energy efficiency rating. So you want to link the data sets so you can study the house value, the address, and the energy efficiency rating. So this is kind of the best case scenario. It's just merging data sets. There's no problems, and then you have a sample, a complete sample. It's a little bit more complicated if the two samples are stratified on using different levels of variables. So then you need to, but again, in the best case scenario, it's a very simple matter. Then you have one stratified random sample, you have a second stratified random sample, you merge them, and then you reweight the final design based on the sampling weights in the first sample and the sampling weights in the second sample. So the key here is for every what is the sample inclusion probability? And this is because the weight in the final survey design is going to be based on the sample inclusion probability. So stratified random samples set up a stratified sampling design, and these determine the weights. And if everyone responds to the survey and there's no failure to respond at the for the entire survey, and in addition there's no failure to respond for individual questions, then it's very simple to construct the sample inclusion probabilities. As everyone who's worked with data knows, that the stratified design is not the final word on the sample inclusion probabilities because of non-response. In this direct record linkage case, there is the possibility of losing information if you throw out records that are not linked. Okay, so that's the first that's kind of the best case for data linkage. The second type of data linkage we've called probabilistic record linkage. Oh, and there is in the econometrics literature, so there's a large literature on data linkage in the statistics, and in econometrics literature there's a smaller literature, but there is a quite useful chapter in the Handbook of Econometrics, and in the paper I think that Sophie circulated, we refer to it. It's by Garrett Ritter and Bob Moffat. It's from about 2004. So some of these terms we've taken from their handbook chapter. So you have direct record linkage, probabilistic record linkage. So you have two surveys. You don't have a unique identifier, but you like to say that statistically this observation is similar to this observation and linked based on the probability that the two are the same. So now the design of the linked data is determined by the designs of the contributing data surveys, as well as by, now because you're linking probabilistically, there's going to be some measurement error produced by linking probabilistically. Under some very strong conditions, you can completely ignore this measurement error. So in the economics literature in the 80s and 90s, people wanted to study the dynamics of consumption, and they didn't have data on consumption over time for a single household. But what they did have is they had cross sections from 1988, 1989, 1990, and they wanted to link probabilistically by creating what in the literature they called a pseudo cohort. And so essentially you match people at age 39 in 1989 to people age 40 in 1990. And essentially, if your model is linear and you're only interested in linear models, you can do that without worrying too much about measurement error. In more general case, it's going to cause some problems with measurement error. Okay, and so that's probabilistic record linkage. Then there's also statistical record linkage. Here you have two surveys, and you have one survey where you have data on some variable x and variable y, and you have a second survey where you have a sample from the same population of variable x and variable z, and you'd like to have a data set that has variable x, y, and z, because you'd like to study perhaps y is an outcome variable and x and z are some input variables. So if it were true that y was statistically independent of z conditional on x, then you could link the data sets statistically and not worry and not have any problems whatsoever. Now, this obviously is a very strong assumption because essentially it rules out kind of correlation. Not essentially, it does rule out correlation between y and z conditional on x. So if you have two data sets, two surveys, survey 1 with x and y and survey 2 with x and z, and you want to create a sample with x, y, and z, if this condition holds, you can simply proceed statistically. If it doesn't hold, but perhaps suppose you have from a different source information about the correlation of y and z, then you can still proceed by bringing that information to bear. So, I mean, this is a strong piece of information about the joint distribution of y and z. It's saying they're independent, but suppose you knew that they were jointly normal and had a correlation that depended on some non-zero correlation. You could proceed in exactly the same fashion. It's a different piece of information, but it's sufficient information to estimate, to do the statistical record linkage. Recently in the economics literature, people have looked at this type of problem and said, well, suppose you didn't know this, but you knew, for example, that the correlation of y and z was bounded. So you know it's a correlation that's bound between -1 and 1. But suppose you knew that it was positive, say, or less than a half. Then you may not be able to estimate precisely a particular regression coefficient or a particular moment in the distribution, but you can estimate a bound on the thing that you're looking to estimate. Okay. Okay. So a little bit about survey design. So what do you do when you link two data sets, perhaps using direct record linkage, and what's the final survey design? So it's useful to go back to the survey design literature, which talks about descriptive inference and analytic inference. So really, when governments first started collecting records at the beginning of the 20th century, they wanted to know, what is the population living in a particular geographic region, or what is the income for tax purposes, things like that. And so they wanted to make inference about the features of a finite population. The population was finite. They wanted to know what is the average income in this finite population. In much economics research, the thing we're after is not inference about a finite population. We're about inference about the process by which the data is generated, which is analytic inference about the infinite superpopulation from which the finite population was drawn as a sample. So there is a finite population. From that finite population, we have a sample, and we have analytically in mind a infinite superpopulation, and we like to estimate, say, the probability density function of some random variable u. So u could be a vector. We use the example x, y, z, and in the statistical record linkage example, we had one survey with values of x and y, and a second with values of x and z. Here's the example I was speaking of earlier. You can think of x as a postal address, y as the market value of a house, z is measures of house quality or energy efficiency ratings. And you might want to know what is the joint impact of x and z on y? Because you'd like to know how much do consumers value energy efficiency. So what's the probability that u lies in some set A? So it's just the integral of the probability density function, or if it was discrete valued, the sum. So if you had a random sample from the population, you could just take that random sample and compute the mean or the variance or whatever other moment. You could non-parametrically estimate the density. But if you have a complex survey design, if you want to estimate the density or some other nonlinear features of the distribution, then you need to use weights. So here's the idea. So those of you who've seen, this is straightforward, just stratified random sampling. How do you reweight? So the true population density is f. We have some weighting function w, and the true population density is f, but what we observe is draws from a density g, and g is proportional to w according to this weighting function. So what we need to do to get an estimate of f is reweight g by essentially dividing by w. So if you observe data on g, the density of the observed data, if you know what w is, then reweighting simply involves dividing g by w, and that'll give you an estimate of f. If you do that, you can use all the standard statistical techniques, linear regression, maximum likelihood methods, method of moments. As long as you know the sample inclusion probabilities, the weights are the W's are the sample inclusion probabilities. This is a straightforward exercise. And that's how you proceed. Now, if the survey is stratified based on some X variable, and suppose you want to estimate the mean of Y conditional on X, you don't need to weight. If the data is stratified solely based on X, conditional on X, you can still estimate the conditional mean and the conditional variance, things like that. So you don't need to weight, but weighting will give you a more efficient, more statistically efficient estimator. So for certain features of your population, if you're interested in certain, usually linear functions of the data, in many cases, and it's all of your analysis is conditional on variables that are used to stratify the sample, unweighted analysis can produce informative information about what you're after. So here's, suppose F again is the density of the population distribution that we're looking to know. We don't know F, we want to estimate F. We have data on G because the probability things are sampled is not strictly random. Now, suppose we just have some function C of F. You could think of C as the mean of the random variable U, or some regression function, some parameters from a regression function, or any functional you want of this unknown density F. If it's true that that function C evaluated at F is the same as the function C evaluated at G, then you don't need to weight. It's more or less trivial, as trivial as that. Whether this happened depends on what particular function C you're looking at, and it depends a bit on the W's it depends on the W's really. Now, strictly speaking, if you want to estimate some conditional mean function, it's possible that theoretically, strictly speaking, you should weight by W in order to get consistent estimates, but it very well may happen that it doesn't matter. You get the same answer whether you weight or whether you don't weight. That happens. That's not that problem. It also may, and as I said on the previous slide, if you want to estimate a conditional mean, for example, and you don't need to weight to get consistent estimate, using the sampling weights can improve the efficiency of your estimate. Okay. Now, what about the survey design of a linked data set? So suppose you have data set 1 and data set 2, and the sample inclusion probability for sample data set 1 is W1, and the sample inclusion probability of data set 2 is W2. Then if the two samples are independent, then the sample inclusion probability of the linked data set, so if there's no errors in linking, and if you don't drop observations from failure to link, then the sample inclusion probability of the linked data set is simply the product of the independent sample inclusion probabilities. So that's kind of the best case outcome, but more generally, linking may introduce additional problems, in which case the correct weights, if you will, to make the sample representative are going to be W1 times W2 times some function. If you have a lot of knowledge of how the linking process works and how observations are dropped or the errors in the linking, you might know some information about L, but more generally, you don't know what L is, so that's a bit of a problem in terms of estimating F. Okay, so in terms of survey design, those really are the main issues. The ideal case, you know the sample inclusion probabilities, and then you simply can reweight and run standard statistical procedures. In reality, though, you may know what the survey designer had some weights that they were attempting to achieve, but then there was non-response problems. Or after you link the data set, you had to drop some observations. So then the weights that the true weights of the final sample that's obtained are not known, essentially because L is not known. What can you do in that case? So the first thing you need to do when that happens is look at the survey, the data that you have at hand, record what is known about the weights, non-response, and the linking process. So what is known about the survey design, and how does it fail to attain the ideal perfect survey design? And in some cases, if they had a lot of resources when they're collecting the data, they may have some information recorded in the survey instrument that tells you information about L. And then you can correct the problem to some degree. Or if you know about non-response rates and how non-response rates vary with U, then you can correct the sampling weights for non-response. So most government surveys or large surveys that are commissioned, they include in their budget resources to measure non-response and account for how it varies with variables in the sample. If you don't know, or if there's limited information about the non-response or the linking errors, the best you can do really is you can proceed and study how sensitive are the results to either running your analysis with weights and without weights. And if you suspect from reading through the information provided by whoever created your data sample, if you suspect that there's problems oftentimes in surveys you have quantitative information in the survey, but then you have qualitative information provided by the data providers about, well, we know that, for example, in supermarket surveys, consumption of alcohol is under recorded. So you can try to so you know the direction of the misreporting or the measurement error or the non-response. Measurement error. So just some basics on measurement error. So suppose U is the true variable we're interested in, but we observe W. W is the simplest case, W is equal to U plus V. V is measurement error. If the measurement error, so classical measurement error is independent, statistically independent of U, and so the relationship between the density of W and density of U is given by this integral equation. So in this case, for example, if you knew that the measurement error was normally distributed, and if you knew the variance, then you could estimate the density of U. If you didn't know it's normally distributed, then there's many different densities of U that could satisfy this equation. However, even if there is measurement error, if you know that suppose you knew that the mean of the measurement error was 0, you could estimate the mean of U just by looking at the mean of W. But you're not going to be able to estimate the variance of U. Now, in a particular case, if you know, essentially based on that measurement error equation here, if you have information about the distribution of the measurement error, the FV, then essentially by inverting this integral equation, you can recover information about the density of U. So that's all the statistical procedures operate based on that observation. In practice, what should you do? You're doing some analysis with some data. The first thing you need to think through is what is known about the measurement error in the data, both in the simple survey and in the linked survey. Is there anything known about the size of the measurement error, or is there anything known about the statistical relationship between the measurement error and the observed not the observed variables, but the variables of interest? So that if there's information known, there's things you can do. Second, if you have multiple measurements with independent errors, then essentially you can average them out to get rid of the measurement error. So multiple measurements can be used to improve upon single measurements. And if neither of those two features can solve the problem, then obviously you can get better measurements if that's feasible within your current resources. In addition, even if measurement error is a problem and you don't know enough to precisely estimate the variable that you're interested in, again, as I spoke about in terms of the previous case where you might know something about the bounds and the correlation, if you know if you have a little bit of information about measurement error, sometimes you can't precisely estimate, say, the mean or variance of u, but you might be able to bound it, or say that it's, yeah, you might be able to bound it. And in it, the other thing one can do is, if you suspect the measurement error might be a problem, you can estimate your model assuming there's no measurement error, and then examine how sensitive your results are to the measurement error. So suppose the variance of v is 0, I can get an estimate of the distribution of u, and then suppose v is normally distributed with variance, and then see how your results change as you increase the variance. How sensitive is the estimate to your estimate of the variance of the measurement error? Okay, so that's pretty much all I have to say about linked datasets at the moment. In this particular report that we put together, we made some recommendations. I mean, the recommendations are really kind of just, I think, statistical best practice. You always want, when you have a data set, you want to attempt to determine what is the design of your final data set. In particular, what are the correct sample inclusion probabilities? You want to understand what are the measurement error properties of all the variables that are the important variables in your data set. And if in your raw data those questions aren't answered to adequately, you'd like to identify what additional information is required to complete these tasks. If you're estimating a linear model, in which case the weights don't matter, perhaps, then oftentimes you can ignore weighting. More generally, you might want to examine how sensitive your results are to weighting. And similarly for measurement error. Okay. So, thank you.
Right.
Thank you very much.
Okay.
Very glad I don't have to link data sets in my research. Is there any questions? Yes.
Can I just say that when you said the question, could you repeat it because you've got the microphone?
Okay.
Yes, please.
Do you distinguish between accuracy and precision? Because in a previous slide, if you could jump up just to your previous slide, your first dot point there with my understanding of terms is that inaccuracy is effectively bias. Imprecision.
I think here, so the question was, am I distinguishing between accuracy and precision? I think on this slide, accuracy, I'm meaning precision.
Okay, thank you.
Yeah.
You mentioned on a much earlier slide that was on statistical record linkage. You said you were noting a case where there were no units in common, but they did both have X measured. So could you clarify for me what you mean by that?
Yeah. So I get the idea would be you have a sample in. You have a sample of the example I gave was houses, and you have one sample. So address is the wrong. Maybe a better example is.
They're anonymized, so you don't have the address anymore.
Yes, thank you. They're anonymized. So you might know you have a sample of houses with a lot of characteristics of the house and the value, and perhaps you know the statistical output area, but you don't know the precise address. So I should have, I misspoke earlier. If you know the precise address, then you're not in the statistical record linkage case. Yeah. Yes?
Sorry, my question was actually following on from that and the nature of X and how it gets created. Is what happens most of the time is that you create a set of different classifications that people are members of, and then they use that as the variable X. Is that what happens most of the time, or is it spatial as you've mentioned before?
It varies a lot. Sometimes it's spatial, and so with spatial data, the coarseness of what is known about the geographic location varies dramatically across data sets. So sometimes you know the statistical output area, sometimes you know the physical address, sometimes you know the the geo coordinates down to the meter. Sometimes you know the city. So it varies a lot in terms of spatial information. In a lot of labor market data sets, the geographic information is only known very coarsely, perhaps at the county level or the city level. And then people will often link based on things like gender, ethnic background, age. So then
make like a composite of the four, and then create some sort of thing that people belong to. Is that?
Yes.
Is that what they do?
Yeah. Or you might know that somebody works for a firm, but you don't know where they work for the firm. So it varies a lot on the application. What on terms of what information you can link based on. So the direct record linkage, you have an ID number, and it's in theory it's unique for everyone in the population. The distinction between statistical record linkage and probabilistic record linkage is not necessarily a black and white distinction. But I think the direct record linkage, you have an ID number which is unique for every member of the population. Yes?
In the simplest case where you have some kind of linking variable, quite often the data sets you're linking will have been collected at different points in time. Could you talk briefly about how one would need to account for the fact that these are collected at different points in time, and particularly where you may have a data set where some variables are highly seasonal and others are not? How can do you have to do variable by variable correction, or how do you adjust for time differences?
So the question was, if you have two data sets collected at different points in time, how do you adjust for differences across time in the data process?